The mystery of the universe in search of the cosmic code. Since the dawn of civilization, people have looked at the night sky and wondered what forces govern the universe. How did the universe come into being? Why do stars shine? And why do galaxies form complex, swirling patterns? For centuries, these questions have driven scientific research and led to countless discoveries that have shaped our understanding of the cosmos. But behind these observations lies a central mystery that continues to elude us: the fundamental code of the universe itself. What laws, equations, and deep principles shape the underlying structure of reality? In this chapter, we embark on a journey to explore the nature of this cosmic code and search for a unified theory that describes everything, from the smallest particles to the vastness of the universe. We delve into the history of scientific discoveries, from Newtonian physics to Einstein's theory of relativity to the fascinating world of quantum mechanics. Each step brings us closer to unlocking the code that will reveal the secrets that hold the universe together. At the heart of the cosmic code lies the language of mathematics. For centuries, scientists have discovered that the universe operates according to precise mathematical laws. Whether it's the orbits of planets, the behavior of light, or the forces of gravity, nature seems to follow rules that can be expressed through equations and numbers. One of the earliest breakthroughs in understanding the universe came from the work of Isaac Newton in the late 17th century. Newton's law of universal gravity described how every object in the universe attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between them. This simple equation could explain everything from the movement of the moon around the Earth to the orbits of distant planets. It was one of the first insights into the mathematical structure of the cosmos. But Newton's laws were just the beginning. As scientists studied the universe more closely, they began to discover deeper and more complex patterns. In the 19th century, James Clerk Maxwell developed a series of equations describing how electric and magnetic fields interact, laying the foundation for the study of electromagnetism. These equations showed that light itself is an electromagnetic wave moving through space at a constant speed. The realization that light, gravity, and other forces can be described by mathematical laws was a major step in our journey to deciphering the cosmic code. But it wasn't until the 20th century that the true complexity of the universe began to emerge. In 1915, Albert Einstein revolutionized our understanding of the universe with his theory of general relativity. In contrast to Newton's idea of gravity as a force between objects, Einstein proposed that gravity is the result of the curvature of space and time itself. Massive objects like planets and stars bend the fabric of space-time, and this curvature affects the movement of other objects. Einstein's famous equation, E equals mc squared, revealed a profound connection between mass and energy and showed that the two were interconvertible. This equation explained why stars shine. They are powered by nuclear fusion, a process that converts mass into energy. General relativity also predicted the existence of black holes, regions of space where gravity is so strong that not even light can escape. These ideas opened the door to a new way of thinking about the universe, in which space and time are not fixed, but dynamic and interrelated. But as revolutionary as relativity was, it didn't tell the whole story. While Einstein's theory worked brilliantly on large scales and described the motion of planets and galaxies, it could not explain the behavior of particles on the smallest scales. To do this, scientists had to turn to a new, even stranger theory: quantum mechanics. If general relativity is the theory of the large, then quantum mechanics is the theory of the small. Developed in the early 20th century by scientists such as Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, quantum mechanics describes the behavior of particles such as electrons, photons, and atoms. But unlike the predictable, deterministic world of classical physics, the quantum world is governed by uncertainty and probability. At the heart of quantum mechanics is the idea of wave-particle duality, which states that particles can appear as both particles and waves. For example, light can behave like a stream of photons, but it can also behave like a wave that can interfere with itself. This duality is one of the many strange features of quantum mechanics that contradict our everyday intuitions. Perhaps the most famous principle of quantum mechanics is the uncertainty principle, formulated by Werner Heisenberg. This principle states that it is impossible to simultaneously know the exact position and exact momentum of a particle. The more precisely you know one thing, the less precisely you can know the other. This inherent uncertainty is not due to measurement limitations, but is a fundamental feature of the quantum world. Quantum mechanics also introduces the concept of superposition, where particles can exist in multiple states simultaneously until they are observed. This idea is famously illustrated by Schrödinger's cat, a thought experiment in which a cat in a box is both alive and dead until someone opens the box and observes it. Despite its strangeness, quantum mechanics is one of the most successful theories in all of science. It explains the behavior of atoms and molecules, the structure of the periodic table, and the properties of light and radiation. It also forms the basis for much modern technology, including semiconductors, lasers, and medical imaging techniques. But quantum mechanics and general relativity are fundamentally incompatible. While relativity describes gravity as a curvature of space-time, quantum mechanics treats gravity as a force mediated by particles, so-called gravitons. This conflict between the two theories has led scientists to search for a deeper theory that can unify them, a theory of everything. One of the greatest challenges in modern physics is the search for a unified theory that can describe all the forces of nature, gravity, electromagnetism, the strong nuclear force and the weak nuclear force, in a single framework. This theory, often referred to as the theory of everything, would be the ultimate expression of the cosmic code and would reveal the underlying principles that govern the entire universe. For decades, physicists have been looking for a way to reconcile general relativity and quantum mechanics. One of the leading candidates is string theory, which proposes that the fundamental building blocks of the universe are not particles, but tiny vibrating strings of energy. These strings can vibrate in different ways, producing the different particles and forces that we observe. String theory also introduces the idea of additional dimensions beyond the familiar 3 dimensions of space and 1 dimension of time. According to string theory, there may be additional hidden dimensions rolled up into incredibly small scales, inaccessible to our current technology. These additional dimensions could be the key to understanding the fundamental nature of reality. Another approach to unifying the forces is loop quantum gravity, which attempts to describe space-time itself as composed of discrete, quantized loops. In this theory, space and time are not continuous, but are made up of tiny, indivisible units, much like the pixels on a computer screen. Despite these promising ideas, a fully developed theory of everything remains elusive. String theory, for example, is incredibly complex and has not yet made any testable predictions that could be confirmed by experiments. Still, the search for a unified theory continues as scientists believe that deciphering the cosmic code will open up new insights into the origin, structure, and future of the universe. What happens if we crack the code? Imagine for a moment that we have successfully deciphered the cosmic code. We would have discovered the fundamental equations that explain everything from the smallest particles to the largest galaxies. What would that mean for humanity? In this thought experiment, we could gain unprecedented control over the forces of nature. We could manipulate gravity, create new forms of matter, and harness the energy of the universe in ways we can only dream of today. Perhaps we could even learn to travel through space-time, visiting distant galaxies, or even alternative universes. But with great knowledge comes great responsibility. Would breaking the code lead to new ethical dilemmas as we gain the power to reshape the universe itself? How would this knowledge change our understanding of life, consciousness, and existence? The implications of deciphering the cosmic code are as vast and complex as the universe itself. The search for the cosmic code is one of the most ambitious and profound tasks in the history of science. From the laws of gravity and electromagnetism to the strange world of quantum mechanics, each discovery brings us closer to understanding the fundamental principles that govern the universe. As we continue to explore the cosmos and develop new theories, we may one day unlock the deepest secrets of reality and reveal the unified theory that describes it all. Black holes, the cosmic giants that bend space and time. Few phenomena in the universe capture the imagination as much as black holes. These mysterious objects, with their immense gravitational pull, are so powerful that not even light can escape their grasp. They bend space and time to their limits, creating regions in the cosmos where the laws of physics collapse. Black holes are not only fascinating as astronomical objects, but also crucial to understanding some of the universe's deepest mysteries, including the nature of space-time, gravity, and even the origins of the universe itself. In this chapter, we will examine the formation, properties, and effects of black holes. We delve into the science behind these cosmic titans, from the mathematical equations that describe them to the observations that confirm their existence. We will also explore the role that black holes play in the evolution of galaxies, as well as their connection to the most extreme events in the universe, such as gamma-ray bursts and neutron star mergers. Most black holes are formed by the death of massive stars. When a star much larger than our Sun runs out of nuclear fuel, It can no longer hold its own against the force of gravity. The outer layers of the star are shed in a massive explosion, a supernova, while the core collapses under the powerful gravitational pull. If the core is massive enough, typically more than about 3 times the mass of the Sun, it collapses into a black hole. This process occurs when gravity overcomes all other forces that could prevent collapse. Even neutron pressure, which normally prevents neutron stars from collapsing further, cannot stop the core from shrinking to a point of infinite density known as a singularity. At the singularity, the physical laws we know stop working, and space and time themselves become infinitely curved. The singularity is surrounded by the event horizon, the point beyond which nothing, not even light, can escape the black hole's gravitational pull. The event horizon marks the point of no return, and once something crosses this limit, it is trapped inside the black hole forever. Black holes come in different sizes. Stellar black holes, formed by the collapse of individual stars, typically have masses ranging from about 3 to several dozen solar masses. There are also intermediate mass black holes, estimated to have masses between hundreds and thousands of solar masses, although their origins are still being researched. And then there are supermassive black holes, whose masses range from millions to billions of solar masses. These supermassive black holes are found at the center of most galaxies, including our own Milky Way. While stellar black holes are fascinating, supermassive black holes dominate the cosmic landscape. These giants, located at the centers of galaxies, can have masses of millions or even billions of suns. One of the best-known supermassive black holes is Sagittarius A, SGR-A, located in the heart of the Milky Way, about 26,000 light-years from Earth. Sagittarius A has a mass of about 4 million solar masses and plays a central role in the dynamics of our galaxy. Supermassive black holes are thought to have formed in the early universe, possibly through the direct collapse of massive gas clouds or through the merger of smaller black holes. Over time, these black holes grew through accretion of gas and dust, as well as mergers with other black holes during galaxy collisions. The process by which they grow is still the subject of active research, but what we do know is that supermassive black holes are closely linked to the galaxies in which they reside. One of the most exciting discoveries in recent years has been the observation of quasars powered by supermassive black holes. Quasars are among the brightest objects in the universe, emitting enormous amounts of energy as gas and dust spiral into the black hole, heating up and releasing light across the electromagnetic spectrum. The energy output of a quasar can be thousands of times greater than that of an entire galaxy, making them the most energetic phenomena in the universe. Black holes are not only fascinating because of their size and power, but also challenge our understanding of space and time. One of the most well-known aspects of black hole physics is time dilation, a phenomenon predicted by Einstein's general theory of relativity. As an object approaches a black hole's event horizon, time slows down relative to an outside observer. From the perspective of a distant observer, It appears as if the object takes an infinitely long time to cross the event horizon, even though time passes normally for the object itself. This effect becomes more extreme the closer an object gets to the singularity. Near the event horizon, the curvature of space-time becomes so extreme that time itself practically stands still. This leads to one of the most bizarre consequences of black hole physics: spaghettification. Spaghettification, also known as the tidal stretching effect, occurs because the gravitational force near a black hole is much stronger at the point closer to the event horizon than at the point further away. For example, if a person were to fall feet first into a black hole, the gravitational force on their feet would be much stronger than on their head, causing them to be stretched into a long, thin shape, similar to spaghetti. Eventually, the tidal forces would become so extreme that the person would be torn apart before even reaching the singularity. This mind-numbing aspect of black holes shows just how strange and extreme the universe can be. The closer you get to a black hole, the more space and time become distorted, and the laws of physics we know fail. Despite their immense power and gravitational pull, black holes are not eternal. In the 1970s, physicist Stephen Hawking made a groundbreaking discovery. Black holes can slowly lose mass and energy through a process now known as Hawking radiation. This phenomenon occurs due to quantum mechanical effects near the event horizon, where pairs of particles are constantly created and destroyed. According to quantum mechanics, pairs of virtual particles constantly appear and disappear from nowhere. Near a black hole's event horizon, one of these virtual particles may fall into the black hole while the other escapes into space. When this happens, the black hole loses a tiny amount of mass because the energy to create the escaped particle comes from the black hole's mass. Over time, this process causes the black hole to slowly shrink and lose mass. For most black holes, this process is incredibly slow, and it would take longer than the current age of the universe for a stellar black hole to completely evaporate. However, for smaller black holes, such as those that may have formed in the early universe, the evaporation process could be much faster. These primordial black holes could be vaporizing right now, releasing a burst of energy as they disappear. Hawking's discovery was revolutionary because it showed that black holes are not completely black after all. They radiate energy, lose mass, and ultimately evaporate. This raises profound questions about the fate of information falling into a black hole and leads to one of the greatest unsolved mysteries in theoretical physics: the black hole information paradox. One of the most puzzling aspects of black hole physics is the information paradox, a problem arising from the combination of quantum mechanics and general relativity. According to quantum theory, information, that is, the complete description of a physical system, cannot be destroyed. However, if a black hole completely evaporates through Hawking radiation, what happens to the information about everything that fell into the black hole? In classical general relativity, any information that crosses the event horizon is lost to the universe. However, this contradicts the principles of quantum mechanics, which state that information must be preserved. This paradox has sparked intense debate among physicists and inspired new theories about the nature of space-time and quantum gravity. Some proposed solutions to the information paradox include the idea that the information is somehow encoded on the event horizon itself, in what is known as the holographic principle. This principle suggests that all information about the three-dimensional universe could be stored in a black hole on the two-dimensional surface of the event horizon, similar to a hologram. Others have proposed more radical ideas, such as the existence of wormholes or quantum entanglements, which could allow information to escape a black hole. While no definitive solution to the information paradox has been found, it remains one of the most fascinating challenges in modern physics, with the potential to fundamentally change our understanding of the universe. Despite their reputation as cosmic destroyers, black holes also play a crucial role in the formation and evolution of galaxies. In particular, supermassive black holes are thought to influence the growth and structure of galaxies, including star formation and the distribution of gas and dust. When a supermassive black hole accumulates matter, it releases enormous amounts of energy in the form of jets and winds. These jets, which can span thousands of light years, sweep through the surrounding galaxy, heating gas and preventing it from cooling and collapsing into new stars. This process, known as feedback, helps regulate the growth of galaxies and prevents them from becoming too massive. The relationship between black holes and galaxies is a symbiotic one. As black holes grow through the accretion of matter from their host galaxies, they simultaneously shape the galaxies themselves through their energetic feedback. This connection is evident in the M-sigma relation, an observed correlation between the mass of a supermassive black hole and the velocity distribution of stars in its host galaxy. This correlation suggests that the formation and growth of galaxies is closely linked to the presence of supermassive black holes at their centers. Imagine you're an astronaut on a mission to study a black hole up close. As your spacecraft approaches the event horizon, you will feel the intense gravitational pull of the black hole. Time slows for you as mission control on Earth observes you floating, seemingly frozen in time, just above the event horizon. From your perspective, however, time passes normally. You watch the stars in the distance stretch and distort due to the curvature of space-time around the black hole. The closer you get to the event horizon, the more you feel your body begin to stretch. The gravitational force on your feet is much stronger than on your head. You become spaghettified, stretched thinner and thinner until you finally cross the event horizon and disappear from the observable universe. What happens next is unknown. Do you continue to fall towards the singularity, where space and time become infinitely curved? Or is there some unknown quantum effect occurring that prevents you from ever reaching the singularity? This thought experiment highlights the strange and mysterious nature of black holes, where the known laws of physics break down and the unknown reigns. Black holes are among the most extreme and fascinating objects in the universe. From their formation through the collapse of massive stars to their role as cosmic architects in the evolution of galaxies, black holes challenge our understanding of space, time, and gravity. They expand the boundaries of what we know about the universe and reveal the hidden depths of the cosmic code. As we continue to study black holes through both observational and theoretical research, we may gain new insights into the fundamental nature of reality. Black holes are not just objects of destruction. They are cosmic laboratories in which the laws of physics are tested to their limits. By studying black holes, we could one day unlock some of the universe's deepest mysteries, from the nature of space-time to the fate of information itself. In the next chapter, we will explore the phenomenon of gravitational waves, ripples in the fabric of space-time caused by the acceleration of massive objects such as black holes. These waves carry information about some of the most violent events in the universe and offer us a new way to explore the cosmos. Gravitational waves, the waves of the cosmos. In the early 20th century, Albert Einstein's general theory of relativity fundamentally changed our understanding of gravity. Instead of viewing gravity as a force, as Newton had done, Einstein showed that it is a consequence of the curvature of space and time, or space-time, caused by the presence of mass and energy. One of the most exciting predictions of general relativity is the existence of gravitational waves, ripples in the fabric of space-time that arise from massive, accelerating objects. For almost a century, gravitational waves remained purely theoretical because they were extremely difficult to detect. But in the year 2015, a breakthrough occurred when the Laser Interferometer Gravitational Wave Observatory, LIGO, detected gravitational waves for the first time. This discovery opened a new window into the universe and allowed us to observe some of the most energetic and violent events in the cosmos, such as black hole collisions and neutron-star mergers. In this chapter, we will explore the nature of gravitational waves, how they are discovered, and what they reveal about the universe. We also look at how gravitational waves help scientists decipher the cosmic code, providing new insights into black holes, neutron stars, and even the early universe. What are gravitational waves? Gravitational waves are ripples in the curvature of space-time caused by the acceleration of massive objects. These waves travel at the speed of light and carry information about the events that created them. They are comparable to the ripples that appear on the surface of a pond when you throw a stone into it. In this case, the pond is space-time itself, and the stones are massive objects like black holes, neutron stars, and supernovae. Gravitational waves are incredibly weak, which is why they went undetected for so long. Even the most energetic gravitational waves cause only tiny distortions in space-time, changes so small that they are measured in fractions of the diameter of a proton. Despite this difficulty, the discovery of gravitational waves was a monumental success because it confirmed an important prediction of general relativity and gave us an entirely new way of observing the universe. There are several sources of gravitational waves, including when two black holes orbit each other and eventually merge, they produce powerful gravitational waves. Detection of such events has provided valuable insights into the properties of black holes. The collision and merger of neutron stars, the incredibly dense remnants of exploded stars, also produce gravitational waves. These events provide a unique insight into the behavior of matter at extreme densities. When massive stars explode into supernovae, They send shock waves through space-time and create gravitational waves. Studying these waves can help scientists understand the mechanisms behind these violent star deaths. Gravitational waves could also have emerged during the birth of the universe itself, in the moments after the Big Bang. Detection of these primordial gravitational waves could provide clues about conditions in the earliest moments of the universe. Detecting gravitational waves requires extremely sensitive instruments capable of measuring tiny distortions in space-time. The world's most advanced gravitational wave observatories are the LIGO detectors, located in Washington and Louisiana in the United States. These detectors consist of two long arms arranged at right angles to each other, forming an L-shaped interferometer. Each arm is 4 kilometers long, and lasers are used to measure changes in the distance between mirrors at the ends of the arms. When a gravitational wave passes through Earth, it causes space-time to stretch and contract slightly, changing the distance between the mirrors and the interferometer. By measuring these tiny changes, LIGO can detect the passage of gravitational waves. However, because gravitational waves only cause incredibly small distortions, the measurements must be incredibly precise, accurate to within a 10,000th of the width of a proton. The first detection of gravitational waves occurred on September 14, 2015, when LIGO observed the merger of two black holes located approximately 1.3 billion light-years away. This event, known as GW150914, was the first direct detection of gravitational waves and provided the first observation of a black hole merger. The signal lasted only a fraction of a second, but it was enough to confirm an important prediction of general relativity. Since this initial discovery, LIGO has made numerous other detections, including neutron star mergers and additional black hole collisions. Each of these discoveries has provided new insights into the properties of black holes, neutron stars, and the dynamics of space-time itself. In addition to LIGO, other gravitational wave observatories have been developed around the world, including the Virgo detector in Italy and the upcoming Kagra detector in Japan. Together, these observatories form a global network of gravitational wave detectors, allowing scientists to determine the locations of gravitational wave sources with greater accuracy. One of the most fascinating aspects of gravitational waves is that they allow us to hear the universe in a completely new way. Unlike light, which is blocked or absorbed by matter, gravitational waves penetrate everything and carry information about events that would otherwise have remained hidden. By detecting gravitational waves, scientists can observe phenomena invisible to traditional telescopes, such as black hole mergers. Detecting gravitational waves is often likened to opening up a new sense, like suddenly being able to hear after previously only being able to see. Each gravitational wave event produces a characteristic chirp, a rising sound that scientists can listen to and analyze. The pitch and duration of the chirping provide information about the masses of the objects involved and their distance from the Earth. For example, the gravitational wave signal from the first detected black hole merger, GW150914, lasted about 0.2 of a second. During that brief moment, the two black holes spiraled toward each other and collided, ending in a final gravitational wave explosion as they merged into a single larger black hole. By analyzing the frequency and amplitude of the signal, scientists were able to determine the masses of the black holes and the energy released during the event. Gravitational waves have revolutionized our understanding of black holes. Before the detection of gravitational waves, black holes were only detected indirectly through observations such as the movement of stars around invisible objects or the emission of X-rays from material falling into a black hole. Gravitational waves, on the other hand, provide direct evidence of black holes by allowing us to observe their collisions and mergers. One of the most surprising discoveries in gravitational wave astronomy was the existence of intermediate mass black holes, which are larger than stellar black holes, but smaller than supermassive black holes. These black holes, with masses ranging from a few hundred to a few thousand solar masses, were difficult to detect before the development of gravitational wave observatories. The detection of intermediate mass black holes suggests that there may be a much wider range of black hole sizes than previously thought. Gravitational waves have also provided new insights into the formation of black holes. By studying the mass and rotation of the black holes involved in mergers, scientists can learn more about the processes that give rise to these objects. For example, some black holes could be formed by the collapse of massive stars, while others are formed by the merger of smaller black holes. Gravitational wave data allows scientists to test these models and refine our understanding of black hole evolution. In addition to black hole mergers, gravitational waves have also provided valuable insights into neutron stars, the incredibly dense remnants of exploded stars. Neutron stars are the densest objects in the universe outside of black holes, with a mass greater than that of the Sun, packed into a sphere just a few kilometers across. In the year 2017, LIGO and Virgo discovered the first gravitational waves from a neutron star merger. This event, known as GW170817, was accompanied by a gamma-ray burst and a kilonova, a bright explosion that occurs when neutron stars collide. By detecting both gravitational waves and electromagnetic radiation from this event, scientists were able to study the properties of neutron stars in unprecedented detail. The merger of neutron stars also provided new insights into the formation of heavy elements such as gold and platinum. When neutron stars collide, they eject large amounts of matter into space, where it undergoes rapid nuclear reactions that produce heavy elements. This process, known as the R process, is thought to be responsible for the creation of much of the heavy elements in the universe. The detection of GW170817 confirmed that neutron star mergers are one of the main sources of these elements. Gravitational waves could also be the key to understanding the early universe. Shortly after the Big Bang, the universe went through a period of rapid expansion known as inflation, during which space itself expanded faster than light. This period of inflation would have produced primordial gravitational waves, ripples in space-time that carry information about the universe's earliest moments. Detection of these primordial gravitational waves would provide a direct insight into the conditions of the early universe and allow scientists to test theories about inflation and the Big Bang. Although these waves are too weak to be detected by current observatories, future space-based gravitational wave detectors, such as the planned Laser Interferometer Space Antenna, LISA, could detect them. If these primordial gravitational waves were discovered, it would be a major breakthrough in cosmology and would provide new insights into the origins of the universe and the fundamental forces that shaped its evolution. Imagine you are an astronaut riding the crest of a gravitational wave as it travels through the universe. As you move through the cosmos, you feel space and time itself being stretched and compressed. The wave carries you through galaxies, past stars and planets, unaffected by the matter around you. You hear the distant collisions of black holes, their signals carried through the cosmos in the form of gravitational waves. As you ride the wave, you become aware that you are experiencing a part of the universe that has remained hidden from human senses for millennia. You will witness events that took place billions of light years ago, events that would otherwise be invisible. Gravitational waves reveal the hidden dynamics of the cosmos and offer a new way to explore the universe. This thought experiment highlights the power of gravitational waves to transform our understanding of the universe. By listening to these cosmic waves, we reveal new layers of reality and gain insight into some of the most violent and mysterious phenomena in the universe. The discovery of gravitational waves marks the beginning of a new era in astronomy. These waves allow us to observe the universe in ways that were previously impossible, revealing hidden phenomena and providing new insights into the nature of space-time, gravity, and the evolution of the cosmos. As we continue to discover more gravitational waves, we will learn even more about black holes, neutron stars, and the early universe. Each new discovery brings us one step closer to cracking the cosmic code and revealing the deep principles that govern the behavior of the universe. Gravitational waves have opened a new window on the cosmos, and the discoveries they bring promise to transform our understanding of the universe for generations to come. In the next chapter, we address the ultimate question: what lies beyond the universe? Is there an edge to the universe, or does it extend infinitely? Could there be other universes beyond our own? Join us as we explore the boundaries of the cosmos and the mysteries that lie beyond. What lies beyond the universe? Exploring the edge of the cosmos. For thousands of years, humanity has looked at the night sky and wondered about the nature of the universe. How big is it? Does it have a border? And perhaps most fascinating, what lies beyond that? As we have developed increasingly sophisticated tools for observing the cosmos, we have learned a lot about the structure, expansion, and evolution of the universe. Yet some of the most fundamental questions remain unanswered. Is the universe expanding infinitely, or is there a limit? Could there be other universes beyond our own? And if so, what does that mean for our understanding of existence itself? In this chapter, we will explore these deep questions about the nature of the universe and the possibility of what lies beyond it. We delve into the theories of cosmic inflation, the multiverse, and the idea of parallel realities. We will also consider the possibility that the universe is finite but unlimited, a concept that challenges our ideas about space and time. One of the most important discoveries in modern cosmology is that the universe is expanding. This expansion was first observed in the 1920s by Edwin Hubble, who noticed that distant galaxies were moving away from us, and their light was shifted toward the red end of the spectrum. This redshift was evidence that space itself was expanding, carrying galaxies away from each other. Today, we understand that the universe has been expanding since the Big Bang about 13.8 billion years ago. The key implication of the expansion of the universe is that there is no fixed center of the universe, nor is there an edge. Instead, space expands equally in all directions, carrying the galaxies with it. If the universe had an edge, we would expect to see some sort of boundary or terminating point somewhere where galaxies and space-time end. But no such limit has been observed. Instead, the universe appears to be both homogeneous, the same in all directions, and isotropic, appearing the same from every perspective. The lack of an observable edge leads to a perplexing question. As the universe expands, what is it expanding into? The answer, according to current cosmological models, is that the universe is not expanding into something. Space itself is expanding. There is no outside the universe because the universe, by definition, includes all of space and all of time. To understand the structure of the universe and what may lie beyond it, we must delve into the theory of cosmic inflation. According to this theory, the universe went through a phase of rapid exponential expansion in the first second after the Big Bang. During this period of inflation, space-time expanded at a rate far faster than that of light, stretching the fabric of the universe and smoothing out any irregularities. Cosmic inflation explains why the universe appears so flat and uniform on large scales. It also suggests that the observable universe, the part of the universe we can see with our telescopes, is only a tiny fraction of the entire universe. Beyond the observable universe, there may be vast regions of space-time that we cannot grasp because light from these regions has not yet had time to reach us. These regions could contain galaxies, stars, and other structures similar to those in our own universe, or they could be completely different. The idea that the universe extends far beyond what we can observe raises an intriguing possibility. If the universe is infinite, could there be an infinite number of copies of our own observable universe, each with slightly different physical conditions, histories, or even versions of ourselves? The concept of the multiverse goes one step further than the idea of multiple space-time realms. According to some cosmological theories, our universe may be just one of many that exist in a larger multiverse. Each universe in the multiverse could have different physical laws, constants, and dimensions, leading to a huge variety of possible realities. There are various multiverse theories based on different physical interpretations. In the Level 1 multiverse version, the multiverse arises naturally from the theory of cosmic inflation. In the Level 1 multiverse, space-time extends infinitely beyond the observable universe, and conditions in these distant regions could differ slightly from those in our local universe. In some regions, the galaxies might be arranged differently, while in others the laws of physics might vary. In an infinite universe, every possible arrangement of matter could exist somewhere, leading to the idea that there are infinite copies of our universe. In the Level 2 multiverse, the universe is part of a larger structure called the inflationary multiverse. This idea suggests that different regions of space-time are expanding at different rates, leading to the formation of separate bubble universes. Each bubble universe could have its own set of physical laws and constants. Some could have completely different dimensions, while others could be similar to ours. These bubble universes are separate from each other, meaning we can't travel between them, but they exist as part of the larger multiverse. The many worlds interpretation of quantum mechanics introduces the idea of a Level 3 multiverse. According to this theory, every time a quantum event occurs, the universe splits into multiple branches, each representing a different outcome. For example, if a particle can take two different paths, both paths will be realized in separate branches of the multiverse. In this interpretation, each possible outcome of each quantum event creates a new parallel universe, resulting in an infinite number of alternative realities. The most speculative version of the multiverse is the Level 4 multiverse, which states that every possible mathematical structure corresponds to a physical reality. In this view, every universe exists that can be described by a consistent set of mathematical laws. This means that there could be universes with completely different physical laws, dimensions, and even forms of consciousness. The Level 4 multiverse represents the ultimate diversity of realities, in which every mathematically possible universe exists somewhere in the multiverse. The concept of the multiverse is still highly speculative and remains a topic of debate among physicists. However, if the multiverse exists, it would fundamentally change our understanding of the universe and our place in it. It raises profound questions about the nature of reality, free will, and the limits of scientific knowledge. Another possibility is that the universe is finite, but unlimited. This concept, derived from general relativity, suggests that the universe could be curved so that it has no edges but still has a finite size. A commonly used comparison is the surface of a sphere. If you travel in a straight line on the surface of a sphere, you will eventually return to your starting point without ever encountering an edge. The surface of the sphere is finite, but it has no boundaries. In this model, the universe could be curved like a four-dimensional hypersphere. If you traveled through space in a straight line long enough, you would eventually return to your starting point, having traversed the entire universe without ever encountering an edge. This idea challenges our everyday understanding of space, but it is a plausible solution based on the equations of general relativity. If the universe is finite but unlimited, the question arises as to what, if anything, exists beyond the universe. In some ways, asking what lies beyond the universe might be comparable to asking what lies north of the North Pole. The question itself might have no meaningful answer within the framework of current physics. Imagine you are an explorer embarking on a journey to the edge of the universe. You travel faster than light and move beyond the observable universe into the unknown. As you move further, the galaxies become sparser, and the structure of space appears to stretch and distort. Eventually, you reach what seems like the edge of the universe, a point where the familiar laws of physics no longer apply. But instead of an insurmountable border, you find yourself in a new space-time region, a bubble universe with different physical laws. The stars here shine a different color, and the planets are made of materials you've never seen before. In this bubble universe, time flows differently, and gravity behaves in strange ways. As you continue your journey, you will traverse multiple bubble universes, each with its own unique characteristics. Some universes are similar to your own, while others are so alien that they defy comprehension. In a universe, the speed of light is much higher, allowing you to travel between galaxies in seconds. In another universe, the laws of physics are so different that matter does not exist at all, only pure energy. This thought experiment illustrates the dizzying possibilities of the multiverse and the idea that there could be countless realities beyond our own, each following their own rules. It challenges our understanding of space, time, and existence itself. Although theories about the multiverse and the shape of the universe offer intriguing possibilities, they also highlight the limits of our current understanding. The observable universe is limited by the speed of light, and we can only see as far as light has had time to reach us since the Big Bang. Furthermore, we simply do not know what exists, and our theories remain speculative. The question of what lies beyond the universe may ultimately be unanswerable, at least with our current technology and understanding of physics. Nevertheless, the pursuit of these questions drives scientific research and philosophical reflection. Whether we ever find definitive answers or not, exploring the boundaries of the universe expands the boundaries of human imagination and curiosity. The question of what lies beyond the universe is one of the most profound and challenging mysteries in cosmology. Whether the universe is infinite, part of a multiverse, or finite but unlimited, each possibility raises new questions about the nature of space, time, and existence. As we continue to explore the cosmos, we may one day gain new insights into these mysteries, but for now they remain tantalizingly beyond our reach. The study of the structure, extent, and possible boundaries of the universe is not just a scientific endeavor. It is also a philosophical journey that challenges our understanding of reality and our place in it. As we explore the boundaries of the universe, we are reminded of the immensity and complexity of the cosmos and the many mysteries it still holds. In the next chapter, we will explore another cosmic mystery: dark matter and dark energy, the invisible forces that make up most of the universe. What are these elusive components, and how do they influence the structure and evolution of the cosmos? Join us as we delve into the dark side of the universe. The Dark Universe, exploring dark matter and dark energy. In our quest to understand the universe, one of the most perplexing discoveries is the fact that everything we can see, all the stars, planets, and galaxies, represents only a small fraction of the entire contents of the universe. Most of the universe is made up of dark matter and dark energy, two invisible components that do not emit, absorb, or reflect light. Together, they make up about 95% of the universe, but they are among the greatest mysteries in modern physics. In this chapter, we delve into the dark side of the universe and explore the nature of dark matter and dark energy. These elusive forces shape the structure and fate of the cosmos, influencing everything from the formation of galaxies to the ultimate fate of the universe. What are these invisible components, and how do they fit into the cosmic code we are trying to decipher? The first evidence of dark matter came in the early 20th century, when astronomers noticed something unusual in the movement of galaxies. In the 1930s, Swiss astronomer Fritz Zwicky studied the Coma cluster, a large collection of galaxies, and found that the galaxies were moving too quickly to be held together by visible matter alone. According to the laws of gravity, these galaxies should have flown apart, but instead they were tightly bound together. Zwicky concluded that there must be an invisible form of mass that provides the necessary gravitational force, what he called dark matter. The concept of dark matter gained further support in the 1970s, when astronomer Vera Rubin observed the rotation curves of spiral galaxies. Rubin found that the stars at the edges of galaxies were moving at speeds that could not be explained by visible matter alone. The outer regions of the galaxies were rotating at the same rate as the inner regions, indicating the presence of an invisible halo of dark matter around the galaxy that contributes to the overall gravitational force. Today we know that dark matter makes up about 27% of the universe. It exerts a gravitational influence on galaxies, galaxy clusters, and even the large-scale structure of the universe. Without dark matter, galaxies would not have enough mass to hold themselves together, and the cosmic web of galaxies and galaxy clusters would never have formed. But what exactly is dark matter? Despite decades of research, we still don't know for sure. Dark matter does not interact with light, which is why it is invisible to telescopes. Nor does it interact with ordinary matter through electromagnetic or strong nuclear forces. Instead, it only interacts through gravity and possibly the weak nuclear force, making it incredibly difficult to detect. Several candidates have been proposed for dark matter, including WIMPs, weakly interacting massive particles, axions, and other hypothetical particles. WIMPs are heavy particles that only interact through the weak nuclear force and gravity, while axions are extremely light particles that could interact with photons under certain conditions. Despite extensive searches using underground detectors and particle accelerators, no direct evidence of dark matter particles has been found, at least not yet. Although we cannot see dark matter directly, its gravitational effects are clearly visible on a cosmic scale. Dark matter plays a crucial role in shaping the cosmic web, the large-scale structure of the universe. This web is made up of giant filaments of galaxies and dark matter that extend through the universe, forming clusters and superclusters of galaxies where filaments intersect. Simulations of the evolution of the universe based on the presence of dark matter show that dark matter began to clump together shortly after the Big Bang. These clumps acted as seeds for the formation of galaxies. Ordinary matter in the form of gas fell into the gravitational wells created by dark matter, resulting in the formation of stars and galaxies. Without dark matter, the gravitational pull of ordinary matter alone would not have been strong enough to form galaxies within the time frame we observed. Some of the most dramatic evidence for dark matter comes from observations of galaxy collisions, such as the famous bullet cluster. In this collision, two clusters of galaxies passed through each other, and astronomers found that visible matter, mostly gas, was slowed by the collision, while dark matter passed through unhindered. By analyzing the gravitational effects of this collision, scientists were able to map the distribution of dark matter and show that it is separate from ordinary matter. These observations leave little doubt that dark matter is real, even if its true nature remains elusive. Dark matter is the structure of the universe that holds galaxies and galaxy clusters together, but we are still in the dark about what it actually is. While dark matter explains how galaxies and structures in the universe hold together, it cannot explain one of the most surprising discoveries of the late 20th century: the accelerating expansion of the universe. In 1998, two independent teams of astronomers discovered that distant galaxies were not only moving away from us, but were doing so at ever-increasing speeds. This unexpected acceleration suggested the existence of a mysterious repulsive force now known as dark energy. Dark energy is even more mysterious than dark matter. It is thought to make up about 68% of the universe, but we know almost nothing about it. What we do know is that dark energy exerts a repulsive force that counteracts gravity and drives the accelerated expansion of space. The nature of dark energy remains one of the greatest unsolved problems in cosmology. One possible explanation is that dark energy is related to the cosmological constant, a term introduced by Einstein in his equations of general relativity. The cosmological constant represents a form of energy that is inherent in space itself and causes space to expand. Einstein originally introduced this term to preserve a static universe, but later discarded it when it was discovered that the universe was expanding. Ironically, the discovery of dark energy suggests that the cosmological constant may not have been a mistake after all. Another possibility is that dark energy is not constant, but changes over time. This dynamic form of dark energy, known as quintessence, could evolve as the universe ages, potentially leading to different scenarios for the future of the universe. Whatever its true nature, dark energy has profound implications for the fate of the universe. If dark energy continues to dominate, it could lead to a scenario known as the Big Freeze, in which the universe expands forever, becoming colder and emptier over time. In this future, galaxies would drift further and further apart, stars would fade out, and eventually all matter would become so thinly spread that the universe would become a dark, frozen void. Dark matter and dark energy are often viewed as opposing forces in the universe. Dark matter pulls galaxies together and creates the structure of the cosmos, while dark energy pushes galaxies apart and drives the accelerated expansion of space. Together, these two invisible forces shape the evolution and fate of the universe, but remain some of the greatest unsolved mysteries of modern science. The interplay between dark matter and dark energy raises important questions about the fundamental nature of the universe. Are dark matter and dark energy two separate components, or are they connected in a deeper way? Could they be different manifestations of the same underlying phenomenon? These questions are at the heart of cosmological research, and answering them could provide new insights into the cosmic code. Despite their elusive nature, scientists are actively searching for dark matter and dark energy, using a variety of experimental techniques. For dark matter, subsurface detectors are used to look for interactions between dark matter and ordinary matter. These detectors, like the Xenon 1T experiment, are designed to capture the rare collisions between dark matter and atomic nuclei. So far, these experiments have not discovered dark matter, but each new experiment brings us closer to discovery. Another approach to studying dark matter involves particle accelerators such as the Large Hadron Collider, LHC, at CERN. By colliding protons at incredibly high energies, scientists hope to create dark matter particles or discover new particles that could provide clues about the nature of dark matter. When it comes to dark energy, the challenge is even greater because its effects are only felt on the largest scales in the universe. Astronomers use large-scale galaxy and supernovae studies to map the expansion of the universe and test different models of dark energy. The Dark Energy Survey, DES, and the Euclid mission are two large projects aimed at studying the nature of dark energy and its role in cosmic evolution. These experiments represent the cutting edge of cosmology, and although we have not yet discovered dark matter and do not yet fully understand dark energy, each new observation brings us closer to understanding the mysteries of the dark universe. Imagine for a moment that there was no dark matter and no dark energy. What would the universe look like? Without dark matter, galaxies wouldn't have enough gravity to hold themselves together. Stars at the outer edges of galaxies would fly out into space, and the complex structures of spiral galaxies would dissolve into chaotic clouds of stars. On a larger scale, the cosmic web of galaxies and galaxy clusters would never have taken shape, and the universe would be a much more chaotic and empty place. Without dark energy, the expansion of the universe would slow and eventually stop. Gravity would pull the galaxies back together, and the universe could begin to contract, leading to a big crunch, a scenario in which the universe collapses in on itself and returns to a hot, dense state similar to the conditions of the Big Bang. This thought experiment illustrates how crucial dark matter and dark energy are to the structure and fate of the universe. Although invisible and mysterious, these forces are essential to the evolution of the cosmos and the understanding of the cosmic code. Dark matter and dark energy are two of the most mysterious and important components of the universe. Together, they make up most of the contents of the universe, shaping its structure and driving its expansion. Although we cannot see or touch them, their effects are undeniable, and understanding them is one of the greatest challenges in modern physics. As scientists continue to search for dark matter and study the effects of dark energy, we may one day unlock the secrets of these hidden forces. Cracking the cosmic code of dark matter and dark energy will revolutionize our understanding of the universe and could reveal new levels of reality that we cannot yet imagine. In the next chapter, we turn to another fundamental force shaping the universe, the expansion of space-time. How fast is space expanding, and what does that mean for the future of the cosmos? Join us as we explore cosmic expansion and its role in the history of the universe. The expanding universe, space-time in motion. One of the most remarkable discoveries of the 20th century was that the universe was expanding. This insight comes from the groundbreaking work of Edwin Hubble in the 1920s, who observed that distant galaxies are moving away from us, and the further away they are, the faster they appear to be receding. This red-shifted light from distant galaxies provided the first evidence that space itself is expanding, carrying galaxies with it in all directions. The concept of the expanding universe has fundamentally changed our understanding of space and time. Instead of a static cosmos, we now know that the universe has been expanding since the Big Bang, and that this expansion is accelerating due to the mysterious power of dark energy. But how does this expansion work? What does it mean for the future of the universe? And how fast is the universe expanding? In this chapter, we will explore the nature of the expanding universe, the concept of Hubble's law, and the role of dark energy in driving this expansion. We will also explore the future of the universe, whether it will expand forever or reach a final end. The discovery that the universe is expanding is based on Hubble's law, which states that the speed at which a galaxy is moving away from us is directly proportional to its distance. In other words, the further away a galaxy is, the faster it appears to be receding. This relationship is described by the equation V equals h0 x d, where v is the retreating speed of the galaxy, h0 is the Hubble constant, which measures the expansion rate of the universe, d is the distance to the galaxy. The Hubble constant, h0, is a crucial parameter in cosmology because it quantifies the rate of expansion of the universe. The current value of the Hubble constant is still a matter of debate, as different measurements produce slightly different results. Observations from the Hubble Space Telescope and other missions suggest a value of about 70 kilometers per second per megaparsec, while other methods, such as cosmic background radiation, CMB, measurements, suggest a slightly lower value. This discrepancy, known as the Hubble tension, is one of the unsolved mysteries of modern cosmology. Hubble's law is based on the observation that light from distant galaxies is redshifted, meaning its wavelength is stretched as the galaxies move away from us. This redshift is a direct result of the expansion of space itself, not just the movement of galaxies through space. As space expands, the light waves passing through it are stretched and shift their color toward the red end of the spectrum. To understand the expansion of the universe, one must realize that space itself is expanding, not galaxies moving through space like cars on a road. In this sense, the expansion of the universe is a metric expansion. The distances between points in space increase over time, but the objects themselves, like galaxies, do not expand. A common comparison is the surface of an inflatable balloon. Imagine the galaxies are like dots on the surface of the balloon. As the balloon is inflated, the dots move away from each other, but they remain fixed on the surface of the balloon. Likewise, galaxies move away from each other as space expands, but they do not move in the traditional sense. Rather, the fabric of space itself expands. This expansion has been occurring since the Big Bang and continues to shape the structure of the universe today. The idea that space itself can stretch is a fundamental concept of general relativity, which describes gravity not as a force, but as a curvature of space and time caused by mass and energy. In the context of an expanding universe, space-time is not static but dynamic, evolving over time as the universe grows larger. While the expansion of the universe was well established by the mid-20th century, another major discovery in the late 1990s led to a fundamental shift in our understanding of cosmic expansion. The realization that the expansion of the universe is accelerating. This surprising discovery came from observations of distant type Ia supernovae, which serve as standard candles in cosmology because their intrinsic brightness is well known. By comparing the observed brightness of these supernovae with their redshift, astronomers found that the most distant supernovae were dimmer than expected, suggesting that the expansion of the universe had accelerated over time. This accelerated expansion implies the presence of a repulsive force that counteracts gravity, called dark energy. As we discussed in the previous chapter, dark energy makes up about 68% of the total energy content of the universe and exerts a repulsive force that causes space to expand faster and faster. The discovery of dark energy has profound implications for the future of the universe. If dark energy continues to dominate, the universe will expand faster and faster, which could lead to a future in which galaxies become so far apart that they become isolated in the vastness of space. Eventually, even the galaxies we can observe today will disappear beyond the cosmic horizon, leaving us in a dark and empty universe. What does the future hold for an expanding universe? There are several possible scenarios, each depending on the nature of dark energy and the overall mass energy content of the universe. The most widely accepted scenario is the Big Freeze, also known as the thermal death of the universe. In this future, the universe will continue to expand forever, powered by dark energy. As galaxies move further apart, star formation will stop, and the existing stars will use up their fuel and die, leaving behind cold remnants such as white dwarfs, neutron stars, and black holes. Over trillions of years, even the black holes will evaporate through Hawking radiation, and the universe will become a cold, dark void filled with isolated particles and radiation. Another possible, albeit more speculative scenario, is the Big Rip. In this future, dark energy grows stronger over time, resulting in a rapid and violent acceleration in the expansion of the universe. Eventually, dark energy would overwhelm all other forces and tear apart galaxies, stars, planets, and even atoms. The Big Rip would result in the complete destruction of all matter in the universe. This scenario depends on the nature of dark energy, particularly whether it exists in the form of phantom energy, an extreme version of dark energy that grows stronger as the universe expands. A third possible scenario is the Big Crunch. Although the discovery of dark energy makes this scenario less likely, it remains a possibility if dark energy reverses or weakens in the distant future. In the Big Crunch, the expansion of the universe would slow and eventually reverse, causing the universe to contract. Galaxies would collide and merge, and the universe would become hotter and denser. Ultimately, all matter would collapse into a single point, similar to conditions at the Big Bang. The Big Crunch could potentially lead to a cyclical universe in which the end of one universe is followed by the birth of a new universe in a big bounce. In the cyclic universe or Big Bounce scenario, the universe goes through a series of expansions and contractions. After each Big Crunch, a new Big Bang occurs, ushering in the creation of a new universe. This model suggests that the universe has no definitive beginning or end, but is part of an eternal cycle of birth, growth, and collapse. Although this idea is intriguing, it remains highly speculative and has not yet been confirmed by observational data. Each of these scenarios represents a different vision for the future of the universe, and the true fate of the universe depends on the properties of dark energy that we are still trying to understand. As the universe continues to expand, what is known as the cosmic horizon emerges, the maximum distance from which light can reach us within the age of the universe. Beyond this cosmic horizon, the light from distant galaxies has not yet had enough time to reach us, and as the universe expands, more and more galaxies will cross this horizon and disappear from our field of vision. In the distant future, galaxies that are currently visible will drift beyond the cosmic horizon, leaving only our local group of galaxies, including the Milky Way and Andromeda, visible. Eventually, even these galaxies will become undetectable as the universe becomes darker and emptier. This concept of the cosmic horizon raises profound questions about the limits of our knowledge. As the universe expands, regions of space may exist that we can never observe, and the true size and nature of the universe may remain forever beyond our reach. Imagine you are on board a spaceship that can travel faster than light. You embark on a journey to reach the edge of the universe, but as you travel, the universe continues to expand. Galaxies that once seemed within reach are getting further and further away, and the space between them is expanding faster than you can travel. No matter how fast you move, the expansion of the universe always outpaces you. The more you travel, the more distant galaxies slip across the cosmic horizon and disappear from view. Eventually, you realize that the edge of the universe is an illusion. There is no limit, no end, just the infinite stretch of space-time. This thought experiment illustrates the nature of the expanding universe. It is not a static entity with a fixed boundary, but a dynamic system in which space itself moves. The concept of an edge becomes meaningless in a universe that is constantly expanding. The discovery of the expanding universe has revolutionized our understanding of the cosmos and opened new avenues for exploring the nature of space, time, and dark energy. As we continue to study the expansion of the universe, we face profound questions about the ultimate fate of the cosmos and our place in it. The expansion of the universe is not just a scientific curiosity. It is a fundamental part of the cosmic code that governs the behavior of space and time. Whether the universe will expand forever, tear itself apart, or collapse in on itself remains one of the most fascinating mysteries in modern cosmology. In the next chapter, we will examine another critical component of the cosmic code, the laws of quantum mechanics and their role in shaping the universe at the smallest scales. How do quantum phenomena influence the behavior of particles and the nature of reality itself? Join us as we delve into the strange and unpredictable world of quantum physics. The quantum universe, deciphering the smallest secrets of reality. As we continue to explore the vastness of the cosmos, we must also look within to understand the universe at its smallest scales. This is where quantum mechanics comes into play. Quantum mechanics governs the behavior of particles at atomic and subatomic levels and is one of the most successful and revolutionary theories in all of science. But it is also one of the strangest, as it upends many of our intuitive ideas about how the world works. In this chapter, we delve into the world of quantum mechanics and explore its role in the cosmic code. We'll look at the fundamental principles of quantum theory, from wave-particle duality to the uncertainty principle, and how these concepts shape the behavior of particles and fields. We will also explore the connection between quantum mechanics and the larger structures of the universe, from black holes to the early moments of the Big Bang. One of the most famous and confusing aspects of quantum mechanics is the concept of wave-particle duality. This principle states that particles such as electrons and photons, the particles of light, can exhibit both particle and wave behavior depending on how they are observed. For example, light can behave like a wave that propagates and interferes with itself, as shown in the famous double-slit experiment. In this experiment, light passing through two narrow slits creates an interference pattern on a screen, as if it were a wave passing through both slits at the same time. However, when individual photons are sent through the slits, they appear to behave like particles and hit the screen one after the other. Amazingly, photons sent individually also produce an interference pattern over time, suggesting that each photon somehow knows that both slits are present, even though it only passes through one. This strange behavior is not limited to light. Electrons, which we normally think of as particles, also exhibit wave-like behavior. When electrons are shot through the double-slit apparatus, they too produce an interference pattern that reveals their wave-like nature. However, if we try to measure which slit an electron passes through, the interference pattern disappears and the electron behaves like a particle. This demonstrates the fundamental mystery of quantum mechanics. The act of measurement influences the outcome of an experiment. Wave-particle duality is a key component of quantum theory and challenges our classical understanding of particles as discrete, localized objects. In the quantum world, particles are described by wave functions, mathematical functions that represent the probabilities of a particle's position, momentum, and other properties. These probabilities only become definitive values when a measurement is made, leading to the famous phrase, "A particle exists in a superposition of states until it is observed." Another cornerstone of quantum mechanics is Heisenberg's uncertainty principle, which was formulated by physicist Werner Heisenberg in the 1920s. This principle states that certain pairs of physical properties, such as a particle's position and momentum, cannot both be known at the same time with perfect accuracy. The more precisely we know the position of a particle, the less precisely we know its momentum, and vice versa. This uncertainty is not due to the limitations of our measuring devices, but is a fundamental property of the quantum world. It arises from the wave-like nature of particles. A particle's wave function propagates in space, so determining its precise location introduces uncertainty in its momentum. The uncertainty principle has profound implications for our understanding of reality. In the classical world, we can measure the position and speed of objects with arbitrary precision, but in the quantum world, there is a fundamental limit to how much we can know about the state of a particle. This limit introduces an inherent randomness in the behavior of particles and forces us to abandon the idea of a deterministic universe. Instead of deterministic laws, quantum mechanics is governed by probabilities. We cannot predict with certainty where a particle will be or what path it will take. We can only calculate the probability of different outcomes. This probabilistic nature of quantum mechanics has led to intense debates about the nature of reality, with some physicists arguing that particles do not have fixed properties until they are observed. One of the most remarkable features of quantum mechanics is the concept of superposition, where a particle can exist in multiple states simultaneously. For example, an electron may be in a superposition of spin-up and spin-down states until a measurement is made. Only when the electron is observed does it collapse into one of the two states. This idea is illustrated by Schrödinger's cat, a thought experiment by physicist Erwin Schrödinger. In this scenario, a cat is placed in a box with a device that has a 50% chance of releasing poison based on a quantum mechanical event. As long as the box is not opened and the cat is not observed, it exists in a superposition in which it is simultaneously alive and dead. The thought experiment highlights the counterintuitive nature of quantum mechanical superposition. Before observation, the system exists in multiple states simultaneously, and the act of measurement leads to a definitive result. Another fascinating phenomenon in quantum mechanics is quantum entanglement, in which two or more particles become correlated such that the state of one particle immediately affects the state of the other, even if they are separated by large distances. This connection, known as non-locality, appears to violate the principle that no information can travel faster than light, a cornerstone of Einstein's theory of relativity. Entangled particles remain connected to each other regardless of the distance between them, so measuring the state of one particle immediately determines the state of the other. This led Einstein to describe entanglement as spooky action at a distance, even though experimental evidence has confirmed that entanglement is a real and fundamental feature of the quantum world. The implications of entanglement are profound. It suggests that the universe is more interconnected than we ever thought, with particles affecting each other in ways that transcend classical logic. Entanglement has also become a cornerstone of emerging technologies such as quantum computing and quantum cryptography, which harness the unique properties of entangled particles for information processing and secure communications. At the heart of quantum mechanics is the idea that particles are not isolated entities, but excitations of underlying fields. This framework is known as quantum field theory, QFT, and provides a unified description of all known particles and forces, with the exception of gravity. In quantum field theory, each particle is associated with a corresponding field that permeates all of space. For example, electrons are excitations of the electron field, and photons, the particles of light, are excitations of the electromagnetic field. Quantum field theory forms the basis of the standard model of particle physics, which describes the electromagnetic, weak and strong nuclear forces, and the particles that mediate these forces. The discovery of the Higgs boson in 2012 confirmed an important prediction of the standard model and provided direct evidence of the Higgs field, which gives particles their mass. Despite its success, quantum field theory remains incomplete. One of the biggest challenges in physics is to develop a theory that unifies quantum mechanics with general relativity, which describes gravity on large scales. Currently, the two theories are incompatible, and a complete understanding of the universe requires a theory of quantum gravity that describes gravity in the quantum realm. Quantum mechanics not only influences the behavior of particles on a small scale, it also plays a crucial role in understanding the universe at large. For example, quantum fluctuations in the early universe are thought to have triggered the formation of galaxies and cosmic structures. During the period of cosmic inflation, tiny quantum fluctuations in matter density were stretched over vast distances, eventually giving rise to the galaxies and galaxy clusters we observe today. Quantum mechanics also plays a key role in the study of black holes. At a black hole's event horizon, quantum phenomena become important, leading to the emission of Hawking radiation, a process by which black holes slowly lose mass. This discovery by Stephen Hawking established the first connection between quantum mechanics and gravity and offered a first glimpse into the possible unification of these two theories in a quantum gravity theory. One of the greatest challenges in modern physics is reconciling the strange, probabilistic world of quantum mechanics with the smooth, deterministic world of general relativity. While quantum mechanics determines the behavior of particles on the smallest scales, general relativity governs the large-scale structure of space-time. Finding a way to unite these two frameworks is one of the goals of theoretical physics and could provide a deeper understanding of the cosmic code. Imagine that the entire universe was in a quantum mechanical superposition, similar to Schrödinger's cat. In this thought experiment, the universe exists in multiple states simultaneously, with each state corresponding to a different outcome of quantum events. Each time a quantum measurement is made, the universe splits into multiple branches, each representing a different result. In one branch you read this script, while in another a different version of you experiences an alternate reality. This thought experiment reflects the many worlds interpretation of quantum mechanics, which states that every possible outcome of a quantum event leads to the creation of a new, parallel universe. If this interpretation is correct, the multiverse could be much larger and more complex than we ever thought possible, with an infinite number of alternate realities coexisting. This raises profound questions about the nature of reality and our place in the universe. Is the universe deterministic, with a single fixed timeline, or is it a branching, probabilistic system in which every possible outcome is realized? The answers to these questions may lie at the heart of the quantum code that governs the cosmos. Quantum mechanics is one of the most successful and at the same time most mysterious theories in all of science. It has revolutionized our understanding of the microscopic world and revealed to us a universe governed by probabilities, superpositions, and entanglements. Despite its success, quantum mechanics remains incomplete, and many questions about the nature of reality, measurement, and the quantum world remain unresolved. As we continue to decipher the quantum code of the universe, we face profound questions about the nature of particles, fields, and space-time itself. Quantum mechanics is not just a theory of small things, it has deep connections to the largest structures in the cosmos, from black holes to the origin of the universe. In the next chapter, we will explore another key aspect of the cosmic code, the search for a theory of everything. Can we find a single theory that unifies quantum mechanics and general relativity and provides a complete description of the universe at all scales? Join us as we delve into the search for a unified theory and the ultimate laws of physics. The theory of everything, the search for the unification of the forces of nature. The history of the universe, from the smallest particles to the largest cosmic structures, is governed by fundamental forces that shape reality as we know it. These forces, gravity, electromagnetism, and the strong and weak nuclear forces, control the interactions between particles and the dynamics of space-time. For decades, physicists have been searching for a theory of everything, TOE, a single framework that unifies all the forces of nature and provides a complete, coherent description of the universe. In this chapter, we will explore the search for the theory of everything, which aims to unite the seemingly incompatible theories of quantum mechanics and general relativity. We'll explore the different approaches physicists are taking to solve this puzzle, from string theory to loop quantum gravity, and look at how these theories attempt to bridge the gap between the very small and the very large. The search for a unified theory is one of science's most ambitious goals, and its success could unlock the deepest secrets of the cosmic code. To understand the search for a unified theory, we must first look at the four fundamental forces that govern the universe. Gravity is the attraction between masses. It is the weakest of the four forces, but acts over the greatest distances and shapes the structure of galaxies, stars, and planets. Gravity is described by Einstein's general theory of relativity, which explains it as the curvature of space-time caused by mass and energy. While general relativity beautifully describes gravity on large scales, it does not fit within the framework of quantum mechanics, which governs the other forces. Electromagnetism governs the interactions between charged particles and is responsible for phenomena such as light, electricity, and magnetism. It is described by quantum electrodynamics, QED, a quantum field theory that combines electricity, magnetism, and light. Electromagnetic forces act over large distances but are much stronger than gravity. The strong nuclear force is responsible for binding protons and neutrons in atomic nuclei. It is the strongest of the four forces, but only works over extremely short distances, on the order of atomic nuclei. The strong force is described by quantum chromodynamics, QCD, a theory that involves particles called quarks and gluons. The weak nuclear force is responsible for processes such as radioactive decay and nuclear fusion in stars. It works over short distances, similar to the strong force, but is weaker. The weak force is described by the electroweak theory, which combines the weak force with electromagnetism at high energies. While quantum mechanics provides a unified framework for electromagnetism, the strong force and the weak force, gravity, remains outside this framework. The challenge is to find a theory that unifies gravity with the other forces and provides a unified description of all fundamental interactions. At the heart of the search for a theory of everything is the conflict between general relativity and quantum mechanics. Both theories are extremely successful in their respective areas. General relativity describes gravity and the large-scale structure of the universe, while quantum mechanics explains the behavior of particles on the smallest scales. However, the two theories are based on very different principles and are fundamentally incompatible. General relativity treats space and time as a smooth, continuous web that is curved by the presence of mass and energy. In this theory, gravity is not a force that acts from a distance, but rather the result of the curvature of space-time itself. Quantum mechanics, on the other hand, describes particles and forces in the form of discrete quantities, quanta, and operates according to the principles of uncertainty, superposition, and entanglement. While general relativity is deterministic, quantum mechanics is probabilistic and introduces an inherent randomness into the behavior of particles. The clash between these two frameworks is particularly evident in extreme conditions, such as inside black holes or in the earliest moments of the Big Bang, where both gravity and quantum effects play a role. In these situations, neither general relativity nor quantum mechanics can provide a complete description of reality, highlighting the need for a unified theory that can bridge the gap between the two. One of the most promising approaches to unifying gravity with the other forces of nature is string theory. String theory states that the fundamental building blocks of the universe are not point-shaped particles, as described in the Standard Model, but rather tiny one-dimensional objects called strings. These strings can vibrate at different frequencies, and their vibrations create the various particles and forces that we observe in nature. In string theory, gravity is not a separate force, but arises naturally from the vibrations of the strings. This offers a potential solution to the conflict between general relativity and quantum mechanics by integrating gravity into the same framework as the other forces. Furthermore, string theory requires the existence of additional dimensions beyond the familiar three dimensions of space and time. These additional dimensions are rolled up to incredibly small scales and are therefore difficult to detect. String theory exists in various forms, but in the 1990s, physicist Edward Witten helped unify these various versions into a single framework known as M-theory. M-theory suggests that the universe may have 11 dimensions, and strings are just one aspect of a more complex, multi-dimensional structure. Despite its elegance and potential to unite the forces of nature, string theory faces several challenges. One of the biggest problems is that string theory has not yet made any experimentally testable predictions. The scales at which string theory operates are so small that they are currently beyond the reach of any particle accelerator or observation instrument. Furthermore, string theory predicts a vast landscape of possible universes, each with different physical laws and constants, raising questions about why our universe has the specific properties we observe. While string theory dominates most of the search for a unified theory, it is not the only approach. Another promising candidate is loop quantum gravity, LQG, which attempts to quantize space-time itself. In LQG, space-time is not a smooth, continuous fabric as described in general relativity, but rather consists of discrete units, or loops. These loops form a network known as a spin network, which represents the geometry of space at the quantum level. Loop quantum gravity offers a way to reconcile general relativity with quantum mechanics without introducing additional dimensions or relying on string theory. One of the central findings of the LQG is that space-time is quantized on extremely small scales, on the order of the Planck length, about 10 to the minus 35 meters. At this scale, the smooth structure of space-time breaks down, and gravity can be described using the principles of quantum mechanics. A major success of loop quantum gravity is its ability to solve the singularity problem in black holes and the Big Bang. In classical general relativity, singularities represent points where space-time becomes infinitely curved and the laws of physics fail. In LQG, however, the quantization of space-time prevents the formation of singularities and offers a possible solution to these extreme conditions. Like string theory, loop quantum gravity is still evolving and faces challenges in making experimentally testable predictions. Nevertheless, it offers an alternative path to unifying the forces of nature and could provide important insights into the quantum structure of space-time. Symmetry plays a central role in the search for a theory of everything. In physics, symmetry refers to the idea that certain physical laws remain unchanged under certain transformations. For example, the laws of physics are independent of whether one moves in one direction or another, or whether one measures a system in one place or another. These symmetries are linked to fundamental conservation laws, such as conservation of energy and momentum. One of the important symmetries that physicists study is supersymmetry, SUSY, a theoretical extension of the Standard Model that proposes a new symmetry between particles and forces. In supersymmetry, each particle has a corresponding superpartner with different quantum properties. For example, the electron would have a superpartner called a selectron, and the photon would have a superpartner called a photino. Supersymmetry offers several advantages in the search for a unified theory. First, it helps resolve some of the mathematical inconsistencies that arise in quantum field theory, particularly in the calculation of particle masses. Second, it provides a natural candidate for dark matter, as the lightest supersymmetric particles could explain the missing mass in the universe. Although supersymmetry is an elegant theory, it has not yet been confirmed experimentally. The Large Hadron Collider, LHC, at CERN is searching for supersymmetric particles, but so far no direct evidence has been found. If supersymmetry is correct, it could play a crucial role in unifying the forces of nature and solving some of the greatest mysteries in cosmology. The ultimate goal of a theory of everything is to develop a theory of quantum gravity, a framework that unifies general relativity with quantum mechanics. Quantum gravity would allow us to describe the behavior of space-time at the smallest scales and provide a complete picture of the universe from the quantum world to the cosmic dimensions. There are several approaches to quantum gravity, including string theory, loop quantum gravity, and other more speculative ideas such as causal set theory and asymptotic security. Each of these approaches offers a different perspective on how gravity and the other forces can be unified, but none have yet been definitively proven. One of the most exciting possibilities in the search for quantum gravity is the potential for new insights into the early universe. Quantum gravity could help explain what happened during the Planck era, the first fraction of a second after the Big Bang, when the universe was so hot and dense that quantum phenomena dominated. It could also provide answers to questions about the nature of space and time themselves, such as whether time had a beginning or whether space-time emerges from more fundamental principles. Imagine if scientists finally discovered the theory of everything. This theory combines quantum mechanics and general relativity and provides a complete description of the universe from the smallest particles to the largest galaxies. With this knowledge, we could predict the behavior of every particle, field, and force in the universe with absolute precision. In this thought experiment, discovering the theory of everything would revolutionize science and technology. We could find new ways to manipulate the fundamental forces of nature, tap unlimited sources of energy, develop advanced quantum computers, and even control gravity. We might even gain insights into the nature of consciousness and life itself, as the theory of everything reveals the underlying structure of reality. But with such knowledge comes profound ethical and philosophical questions. If we could predict the behavior of the universe with absolute accuracy, does that mean that the universe is deterministic and there is no room for free will? And what does it mean for our understanding of reality if the universe is governed by a single, unified code? This thought experiment illustrates the transformative power of a theory of everything. Although we are still far from discovering such a theory, the search itself expands the boundaries of human knowledge and forces us to confront some of the deepest questions about the nature of being. The search for a theory of everything is one of the most ambitious and profound undertakings in all of science. By unifying the fundamental forces of nature, physicists hope to crack the cosmic code and reveal the underlying laws that govern the universe. Whether through string theory, loop quantum gravity, or a yet-to-be-discovered framework, the search for a unified theory is driving research at the frontiers of physics. Even if we don't have the answers yet, the journey to a theory of everything changes our understanding of space, time, and reality. The search for unity in physics is not just solving equations, it's about discovering the deepest truths of the cosmos and our place in it. In the next chapter, we will explore another exciting frontier in physics, the search for additional dimensions and parallel universes. Could hidden dimensions exist beyond our perception? Could our universe be just one of many in a vast multiverse? Join us as we delve into the fascinating possibilities of additional dimensions and the multiverse.